Hello, this is Dr. Benjamin Norris from the Chemistry Department at Frostburg State University. Today we're going to talk about fundamental mechanism steps in organic chemistry. And in the upper right of the screen I have a curved arrow because today we're going to be talking about curved arrow patterns in organic mechanisms. Curved arrows show electron movement in mechanisms. Remember that breaking and forming covalent bonds is all about the electrons in those bonds. And so we show the movement of those electrons with curved arrows. Arrows need to start at electron pairs, lone pairs, sigma bonds, pi bonds. Arrows can end at atoms or bonds. Let's look at a couple of examples. Here's an example where an arrow is starting at the lone pair of the bromide anion. It's being used to form a new bond to carbon atom. Here is an example where an arrow is starting at the boron hydrogen bond, and that pair of electrons is being used to form a new bond to carbon. And an arrow is starting at the carbon-oxygen pi bond and is being used to make a new lone pair for oxygen. Curved arrows can show bonds forming and bonds breaking. Here's that same example with bromide anion and the carbocation. This arrow is showing the lone pair on bromine being used to form a new carbon-bromine bond. Here is an example where an arrow is showing the breaking of a carbon-chlorine bond and the pair of electrons in the carbon-chlorine bond becoming a lone pair on the chlorine atom, making it the chloride anion. Generally, when arrows start at lone pairs, the lone pair is converted into a bond. And when arrows are starting at bonds and pointing towards atoms, we're converting a bond into a lone pair. Curved arrows are always drawn from nucleophiles to electrophiles. The nucleophile donates the electron pair, and arrows have to start on an electron pair. The electrophile accepts that electron pair. The nucleophile always has its formal charge increased by 1 because it's losing electrons to the electrophile. The electrophile always has its formal charge decreased by 1 because it's gaining electrons from the nucleophile. Let's look at some common mechanism patterns. There are 4 common mechanism patterns in organic chemistry: proton transfer, loss of leaving group, nucleophilic attack, and rearrangement. A proton transfer step is nothing more than an acid-base reaction, and we've seen this pattern of mechanism arrows before when we talked about acid-base reactions. A proton transfer step is 2 arrows. One arrow is being drawn from the base to a proton. The other is being drawn from the hydrogen, from the hydrogen into the acid, or to the conjugate base of that acid. And note that our base is a nucleophile and our acid is an electrophile. Loss of leaving group, sometimes called fragmentation because the molecule is breaking up into pieces, usually has 1 arrow, but it sometimes has 2, drawn from a bond to a leaving group. Here is an example of what that might look like. We are drawing an arrow from the carbon-bromine bond to show that that bond is breaking and the electrons are going with the bromine atom. The carbon is left behind with a positive charge, and the bromide anion leaving group gains a negative charge. Loss of leaving group sometimes occurs in conjunction with other mechanism steps. Or sometimes loss of leaving group requires 2 arrows. So here is an example where the chlorine is leaving, the carbon-chlorine bond is breaking, but we're also showing we're also showing lone pair from the oxygen being used to form the pi bond as the chlorine is leaving. This is still a loss of leaving group step, even though we're drawing 2 arrows. You will sometimes see pi bonds forming and breaking in conjunction with other mechanism steps. Nucleophilic attack also generally has 1 arrow, but sometimes 2, from the nucleophile to the electrophile. So here is our example of bromide anion attacking carbocation. We're drawing an arrow from bromide to the carbocation to show that a lone pair from bromine is being used to form a new carbon-bromine bond. the bromine goes from negative charge to neutral, and the carbon goes from positive charge to neutral. The bromine is losing electrons and the carbon is gaining electrons. Here's an example of a pi bond being used as a nucleophile, as the carbon-carbon pi bond, the lone pairs in that, can be used as a nucleophile and do nucleophilic attack on an electrophile. And you'll notice one of our carbon atoms is positively charged because it's losing electrons, and the boron is negatively charged because it is gaining electrons. Here's an example where you might see two arrows in a nucleophilic attack. The boron-hydrogen bond is being used to do a nucleophilic attack at the carbonyl carbon. But the carbonyl carbon already has 4 bonds, and so something has to give way. The carbon-oxygen pi bond can break and become a new lone pair on the oxygen. So as I said in the previous slide, pi bonds can form or break in conjunction with other mechanism steps without changing what that mechanism step is. Finally, there's rearrangement, and rearrangements are usually one arrow showing some group moving from one part of the molecule to another. In this case, we have a carbocation with a positive charge at one position, and we have a hydrogen atom nearby that can hop over and generate a different carbocation. Carbocation rearrangements are the most common type of rearrangements in organic chemistry, and they're enough to warrant their own video describing that behavior. Rearrangements can sometimes happen in conjunction with other steps. So here is a hydrogen shifting in a rearrangement at the same time the carbon iodine bond is breaking in a leaving group. Sometimes we can have combinations of steps. Occasionally you have a reaction where its mechanism is concerted, meaning everything happens at the same time. And in this case you might have more than one mechanism step going on at the same time. Two common cases we will study before we're done with the first semester of organic chemistry are illustrated below. Here is an example of a concerted substitution reaction involving a nucleophilic attack and a loss of leaving group at the same time. The hydroxide anion is attacking the carbon that has the carbon-bromine bond, and the carbon-bromine bond is leaving with the loss of leaving group at the same time. Another concerted reaction we will study is an elimination reaction in which a proton transfer is concerted with a loss of leaving group. And so here a hydroxide anion is doing a proton transfer, and the electrons in the carbon-hydrogen bond are being used to form the new pi bond while the carbon-chlorine bond is breaking and the chloride is leaving as a leaving group. Up next, we'll do a practice session on fundamental mechanism steps. Thank you for watching.